Okay, so a couple of, I guess, quick things. I'm still having an audio problem where all of a sudden it just, I don't know, it records some kind of scraping or popping. I've tried a couple different mics and different setups. I don't know. I can't figure it out. It might be a problem with the sound card, um, but I can't switch to my other computer because then I can't write on the screen, and I'd have to capture audio separately and overlay it. And wow, apologies. I guess we'll just have to live with it for now. But please send me an email or let me know if you guys are having problems going through this stuff, and if there is, if the audio gets too bad. I try and review the videos before they go online, but I kind of just skip around to random places just to just to spot check the audio. So if something goes wrong, please do let me know, and I'll now re-record the video. But anyway, we were going through one of the big topics in this semester, and that's this idea of the aromatic, or I should say, adding things to an aromatic ring. And we had gotten to this idea of what happens when we start to have multiple groups, or how can we add multiple things to the aromatic ring. And we had talked about this idea of ortho and para versus meta directors. And so I wanted to get into talking about the fast versus slow part of this. They're kind of related, and to be honest, when I was going through organic chemistry as an undergraduate, I kind of thought one meant the other. There is a separate idea behind this, and I'll try and talk about it here and bring it out. But there are two parts of this, okay? And so, setting aside the idea of activators and deactivators, excuse me, let me try this again. Setting aside the idea of ortho, para, and meta directors, we also have activators, right, and deactivators. And these are exactly what we think they are. Whether they activate or deactivate the ring towards aromatic substitution, okay? Specifically, electrophilic aromatic substitution. All right, so remember, the electrophilic aromatic substitution is what we've been doing all along. And so just keep that in mind, because we'll learn another mechanism probably in the next video where we'll do nucleophilic aromatic substitution, okay? But different topic. So, okay, activators and deactivators. So when I'm saying that my aromatic ring is activated towards substitution, it means that I have a functional group on that ring which is increasing the rate of that reaction, okay? So if I have an activator, I'm increasing the rate of the reaction, so a faster rate of reaction. So, we got to think about this from the kinetic perspective. And so we could sit here and make some giant argument about kinetics and all this kind of stuff, and the book does a pretty decent job going through all that, and I'm not too interested in that, at least for, the course right here. If we were chemistry majors and, doing all that, then, we'd approach this a little bit differently. So to keep it simple, right, an activator just means I'm going to increase the rate of my reaction for substitution, okay? Now, how does it do this? Here's where we start to get into maybe the subtleties of it. How, right? How do we increase the rate of reaction? And now we really got to think, okay? We really got to think. So, to think, we go to Mr. Generic Reaction, okay? Step one, right? We have our ring attack our electrophile. And then in the last step, right, Mr. Generic Base regens the ring, okay? So if we want to zoom in on this, we really only have two steps, right? Step one, well, let me pick a different color here, right? Just for argument's sake. Wow. Good thing this is recorded on video. Step one and step three. Okay, all right, anyway, you guys got it. Step one and step two. Which one of these is the slow step, right? Which one of these is the slow step? Now, when we're talking about the slow step, what do I mean by that, right? This is the rate determining step, right? This is the step that's the hardest, the biggest hill to climb, right? The one that requires the most energy, right? All these ways are saying the exact same thing, right? Which one is the slow step? So if you recall back to when we were first learning mechanisms with SN1 and SN2, E1, E2, all that kind of stuff, right? We talked about, why do we call something an SN1, right? Why do we call it an SN2, right? Why is it E1? Why is it E2? So that same idea there, right? We talked about we are looking for the rate determining step. So if we think about it, right, really what we're saying is how do we activate or speed up or increase the rate of the reaction? We have to identify the rate determining step. Okay, and if we think about it, it should be pretty obvious. Okay, so here you got two steps here. So you got a 50-50 shot. Okay, so pause, think about this and say, which one of these two steps, the one in red or the one in black, one or two, which one of these two steps do you think would be the most difficult? Okay, so take a quick pause, see if you can answer that question, and then explain why, right? Why would that be the slow and difficult step? So hopefully you guys came up with an idea, right? Or you just read it in the book or watched it somewhere else, or or you called your friend and asked them, right? Whatever way. I think, right? I think that it's obvious that this will be the slow step, okay? Now, why is that, right? Why would that be the slow step? Well, for two reasons, right? Well, really only for one reason. Okay, 1.5 reasons, all right? We'll settle at 1.5 reasons. First reason is we're breaking aromaticity, right? So we've got to take some electrons out of our aromatic system, and that pi bond, right? So let's highlight, right? This pi bond there in red, which is part of the aromatic system, now has to get sent out, right, to attack the electrophile. Excuse me, right? So we're breaking our aromatic ring temporarily. That takes a lot of energy. Remember, generating an aromatic system is a stabilizing effect, okay? Especially for something like benzene. Right? Once we get to the larger aromatic rings, right, there's arguments to be made about that, but, with something like benzene, right, that's a very stabilizing effect. Well, what else are we generating? Well, we're also generating a carbocation along the way. Ooh, right, that's not too good. Hang on a second, I got to pause for two. Oopsies. Sorry, everyone, my allergies are driving me nuts, and so I have to, pause, otherwise you're sneezing at you guys through the video here, so apologies for that. Anyway, so back to what we were talking about. So two things, right? One, we're breaking the aromatic ring. Two, we're generating a carbocation. Okay, those are two things that are kind of take a lot of energy to do. Now, the reason why I was kind of debating about 1 versus 2 versus 1.5 things here, because the argument could be made, right? The argument could be made that, well, we've already had to generate an electrophile. Is that electrophile more or less stable than the formed carbocation? And right, so, and there's, that's certainly an area of debate, and depending on the electrophile that gets formed, right, that's certainly something that we have to consider, okay? So that's why we could say there's really 1 or 2 reasons or 1.5 reasons, it depends. Really, at the end of the day, if we want to simplify, I'd say, hey, look, right, we've got to break apart that aromatic ring, that takes a lot of energy. So, okay, so how can we speed this up? Well, right, we've got to increase the rate at which we are, let's say, capable of breaking that aromatic ring. So let's think about this. What happens here, right? So remember, we're dealing with electrophilic aromatic substitution, okay? So our ring is sending out electrons to hit an electrophile, okay? So if I have more electron density in my ring, it's more negative, right? It's more partially, right? There's more partial negatives, if you want to think about that, right? In my ring, which makes it easier for it to reach out and grab that positive charge, or more susceptible to, or more likely to. Does that make sense, right? So we're saying if we put negative charge onto my ring, it's easier for it to reach out and grab that positive charge. That's the whole idea behind it. Okay? Now, a consequence of this, right? A consequence of this is what we talked about in the previous video, which is the idea of drawing resonance structures and being able to stabilize a carbocation. Okay? But that stabilization, right, let me pause here, right, that stabilization doesn't happen until this step here, which isn't the slow step, right? That's after the slow step, okay? So this is where it gets a little bit tricky, right? And this is why, if you look back, I reminded you guys that resonance structures are simultaneously existent and all this kind of idea behind there, because I'm not that I'm lying to you guys, right? Remember, I'd always promise I'd tell you guys when I lie to you, but, we're maybe bending the truth here a little bit, or kind of overlooking one part of it, okay? But when, right, so let's sum this up here. Okay, so enough of the 100 words. So when we are talking about activators on a ring, we are talking about increasing the rate of that slow step, which is the attack on the electrophile, okay? And what we're looking for, so activating groups, let's call it this, activating functional groups, okay? So let's take a look at the list of activating functional groups. All right, so remember, all of these are bound to an aromatic ring, right? So R can equal an oxide, right? We could have an alcohol, or we could even have our good old buddy Mr. Ether, okay? So an alkoxide, an alcohol, or an ether, directly bound to the ring, are very, very powerful activating groups, okay? They really make the aromatic ring that much more reactive. Okay, that's fine. That sounds good. What else can we have? Okay. Well, we could have amines. We could have amides, and here's where we have to be careful, okay? So when the when the nitrogen of the amide is bound to the ring, it's an activating group. Okay, and this should start to give you guys a hint of what's going on. And alkyl groups are activators. Okay? Okay, so what's the pattern here? Here's the pattern. Okay? Do you guys see the pattern as to why these are activating groups? When the atom bound to the ring has lone pairs on it, when the atom bound to the ring has lone pairs on it, it will activate the ring towards electrophilic aromatic substitution. And it will consequently be an orthopara director. You guys catch that? So, how do we identify activators? You look for lone pairs on atoms that are directly bound to the ring. Because remember, if we can make the ring more negative, it's more likely to do its attack. You say, okay, that makes logical sense. What about alkyl groups? Well, why is this the case? Well, alkyl groups are electron donating, right? Through hyperconjugation and inductive effects, right? We can basically shovel some electrons from alkyl groups into the aromatic ring itself, okay? So inductive and hyperconjugation is what causes alkyl groups to kind of push things into the ring, all right? Now, it should be said, is this, what I just showed you guys here, an exhaustive list of every functional group that could be an activator? No, it is not. I know it is not. Okay, they're on the book, they're online, you guys can look them up, right? So just do a Google search for activating functional groups, and, there's a ton of them there, right? But again, do you really have to memorize this? No, you don't, okay? No, you don't. All you have to do is really look for lone pairs on groups directly bound to the ring. Got it? Now, there should be a functional group that you guys expect to be an activator. Oops, I should. Oh, I did write it up there. Okay, I'm sorry. There's a group that you guys should immediately be thinking of, saying, hey, I know a set of atoms that are, have a lot of lone pairs on them, right? That should be on that list. Well, there is an exception. Okay, so let's take a look at deactivating groups. So same idea here, but from the opposite direction. To deactivate, we want to remove electron density from the ring. Okay? We want to remove electron density from the ring. So there's a couple of groups. Your sulfate groups. You know what? Let me draw this out because I'm going to come back and make my point. Okay. So my sulfate groups, cyano groups, carbonyls, where the carbonyl carbon, right, is directly bound to the ring. So aldehydes, ketones, esters. Okay, so carbonyl groups where the carbon is bound directly to the ring. And then NO2s. Okay, nitro groups are probably the most deactivating. Now, what do you notice about our deactivating groups? Well, each of the atoms bound directly to the ring has a partial positive charge on it. Okay? If you notice, right, each of those atoms is bound to a set of electronegative atoms like oxygens or nitrogens. That's withdrawing electron density away from the ring. Okay? So you're withdrawing electron density away from the ring, so it's deactivating towards substitution. Electrophilic substitution. Okay? Consequently, these things are meta-directors. And let me pick a different color here and talk about halides. Okay, so if we have our good old buddy, let's say, bromobenzene, okay? Two things. Yes, they do have lone pairs. So we would expect them to be activators. But because of their electronegativity, they're actually deactivators. But, so they are deactivating, but ortho-para-directors. Okay? As opposed to here, we have meta-directors for our deactivating groups. And up here, we have ortho-para. Okay? So all activating groups are ortho-para-directors. All deactivators are meta, and our halides are kind of the ones that are caught in between. They deactivate, but they're ortho-para-directors. Okay? Now, if some of you guys pause and think about what I just said, you might come up with some like, hey, wait a minute, something here doesn't quite click, and you're absolutely right. Okay? I'm leaving off a little bit of another discussion to be had. Okay? And I'd be happy to have that discussion with you guys if you want to come by office hours or, do some kind of virtual office hours and talk to you guys a little bit more about the nitty-gritty details here. Okay? But this is the idea. Okay? Activating functional groups, deactivating groups, and then our halides. What you need to be able to recognize these, right? I don't need you guys to memorize it. I need you guys to understand. Okay? With the idea of activating, deactivating, why they are deactivating, why they are activating. Okay? Now, what does it mean, right? What does this mean, and what do we need to care? Well, when we go through, probably during our next in-person, right? During our next in-person or virtual problem session, right? We'll start to do some synthesis, some multi-step synthesis, where we'll have to pay attention to these activating groups and deactivating groups. Okay? But that's it for this video, right? So pause and watch this, or look at the links that I posted for you guys, and make sure you kind of have a good grasp on the idea and the concepts behind this.